size of the specimen is very small for conducting the experiment. Okay, so that is what, if I have only about 0.75 mm diameter. Okay, so 0.75 mm diameter here. Okay, so here you have 0.75 mm diameter. Is it right? So it is out of very small dimensions. It is of very small dimensions. Okay, so now for small dimensions you can get it that it may have some less amount of flaws or less amount of defects. Okay, that means so the quantity or the amount of defectness or the amount of flaws, the amount of so blowholes which are going to be get in the specimens are very low. Okay, so now in relation to that one, so if you consider the size of the component which has to be used in design, of a very bigger size, so then what happens, as the size increases, so you may get some chances of fatigue failure. That means because the probability of the defects inside the component are maybe more. It means existing of blowholes, flaws, or any inner defects are more. Okay, so now for that reason, so as a specimen or as a size, okay, so as the size increases, okay, size increases, so the factor is going to decrease. That means suppose for standard specimen, so the size factor is taken as a 1 here. Okay, size factor is taken as a 1. So if the diameter increases here, let us take diameter as a 15 mm. Now the size factor is going to reduce. Let us go for, it may go for 0.8. Okay, suppose if the size is too much large, around about 1200 diameter, then it may come to 0.6. Okay, clear? So the size factor takes into account as the reduction in endurance limit due to increase in the size of the component. Okay, what is the reason? Reason is it may exist more flow holes or more flaws or more blowholes inside the component. As the size increases, there is a possibility of increase in defects. Okay, so now the size effect factor. Okay, the size effect factor so different books they have used different notations here. Some book they have used it as a KB. Okay, and in data handbook it is a A. So now let us go for the data handbook, design data handbook. Okay, just look out here. Now for so now B is size factor here. Okay, that is what size correction factor, not a A. Okay, B is size correction factor, not A. Okay, so let us just take a correction here. Now the size factor is B here. Okay, size factor is B. In some book they have gone for it as a KS, KB. Okay, they may be used it as a KS, okay, size factor, or KB. Now, so next factor is what, a surface effect or a surface finish effect. Okay. Is what, surface finish factor. Or surface finish effect. Now, so in relation to the specimen preferred, okay, the beam specimen whatever preferred for calculation of or for conducting the experiments, okay, it is of nature mirror finish. It is of nature mirror finish. So the purpose of surface finish is to remove the any scratches or any indentations over the specimen. Okay, suppose if it has any surface scratches or any imperfections, that has to be removed before conducting the experiment. Okay, so now if the component is preferred, okay, now what have done? So the specimen is polished to mirror polish, sorry, mirror finish. Okay, now what happens for conducting experiments? Okay, so you are preferring the specimen to the mirror finish. So as its size is very small, okay, so size is very small, okay, so you can carry over the surface mirror finish polish over the component. Okay, but if consider the cost wise, it is, if you consider the cost wise, so it is impractical to provide such an expensive surface finish for the actual components, because if the size of component is a bigger one, so it will consume lot of amount in terms of money. It is going to consume lot of amount. Okay, so what they will do, so they sometimes, even though components may not require that much of surface finish, even though the components may not require that much of surface finish. Example, if you consider a connecting rod in IC engine, okay, so connecting rod in a IC engine, so you are going to surface finish only the bearing surface here. You are going to surface finish only the bearing surface. Okay, so that means you should not have any frictional surface. It should not have any frictional surface. But you can't going to make this outer portion as an surface finish. Is it right? So you are going to leave this as it is. You are going to leave this as it is. Okay. Now to consider the effect of this surface finish factor, you need to add up factor here. You need to add up factor. So the surface finish factor is I think noted with the letter C here. Okay, noted with the letter capital C. So in some book they have gone for KSR, SUR, KSUR as a notation. Now let us look at in data handbook. Okay, so now C is the surface correction factor. C is the surface correction factor, right? So you can get the value of C from referring table number 2.2. You can get the value of C, that is what surface correction factor, from table number 2.2. Okay, let us look at what is the table number 2.2. Okay, table number 2.2. Now this is the table number 2.1, right? 2.1, 2.2. Okay, so now it depends on ultimate stress here. So the surface finish factors depends on the ultimate stress. Okay, now based on the ultimate stress, okay, and based on the type of material here, whether the material is made of a cold drawn, whether the material is of hot rolled surface. Okay, suppose if you have an 410 ultimate strength, okay, 410 megapascal. If the material is made of cold drawn, then you can select here 0.91 as the surface factor. If it is a hot rolled, then you go for 0.72. Then you go for 0.72. Similarly, if the ultimate strength is of 690 megapascal, okay, ultimate stress is 690 megapascal, then you go for C equal to 0.85 if it is made from cold drawn steel. and 0.55 if it is made from hot rolled surface, that means hot rolled steel. Clear? Now all depends on the type of material you are going to use. Okay, all it depends on type of material you are going to use. Okay, so if it is a cold drawn, you may get more factor. If you have a hard roll, you are going to get a less factor. Okay, next is what the load effect here. Next is load effect. Okay. So the possibility of loads are this is what use of axial load. Okay, axial load, that means so it may subjected to the fluctuating tensile load, or it may subjected to fluctuating compressive loads, or it may subjected to some reversed load, right? One case. So second case is it may subjected to bending load. It may subjected to bending load. Again, in this case, it may subjected to tensile bending load, it may subjected to compressive bending load, or it may subjected to reversed. The last case is what? It is a purely shear load, purely shearing load. Okay. So now in this case, the effect of load is different here. Effect of load is different. So the fluctuation of bending stress and the fluctuation of shearing stresses are entirely different. Okay. So now the effect of load is noted with a letter A here. Noted with a letter A. Okay. So now in this case you need to select only the value of A, referring whether it is subjected to axial load, whether it is subjected to bending load, whether it is subjected to shearing load. Okay. So again, if you come to the reality or practicality application, okay, so the possibility of failures in these cases are different. In these cases are different. Okay. So let us look out to the values here from data handbook. Okay. So now where A is equal to 1, okay, if it is subjected to reversed bending, right, if it is subjected to bending load or bending stress, okay, whether it is maybe fluctuating or whether it may be reversed, then you go for 1. Suppose if it is subjected to reversed axial loading, that means so it may be subjected to combination of a tensile load as well as the compressive load. You can select range of A from 0.7 to 1. 0.7 to 1. Next is 0.5 to 0.6. 0.5 to 0.6 for reversed torsional loading. For reversed torsional loading. Suppose if the component is subjected to shear stresses, fluctuating shear stresses, then the value of A should be how much? In a range from 0.5 to 0.6. Okay. Suppose if it is subjected to axial loading, okay, then you can select from 0.7 to 0.1. If it is reversed bending, then you can select 1. Then you can select 1. Okay. Now, so I'll show where you need to use these equations. Okay. Now these equations, these factors are related to what? The endurance strength. Okay. These equations are related to what? Endurance strength. Now if you want to select the endurance strength for design purpose, okay, for design purpose, okay. Now here, if you want to get the value of endurance strength for design purpose, let us go for sigma E. D is equal to what? Design endurance stress. Okay. Now, so sigma E is what? Endurance strength. Endurance strength. Okay, or endurance stress. Now, as you need to consider effect of all these three parameters, that is what? Size factor, surface factor, as well as loading. Okay. So then the sigma ED, okay, or sigma EA allowable endurance stress equal to what? Sigma E into A into B into C. So, what will get? A, B, C sigma E. Okay. So, let us take an example here. So, if you take a material, that is what, a cold drawn material, of 420 megapascal, okay, of a 420 megapascal. So, now it is subjected to, now it is an axial load, it is subjected to reversed axial load. Now, if it is subjected to reversed axial loading, okay. So, let us consider it has a some size and it has some surface factor. So, now for reversed axial loading, so you can select value of A 0.7 to 1. Okay. So, now in this case I will go for 0.8, A equal to 0.8, okay. So, B equal to 0.95 and C equal to 0.9. Okay. So, now let us calculate what is the allowable value here. Okay. So, now A is how much? 0.8, okay. So, B is 0.95, okay. So, C is 0.9. So, the allowable stress is 420 megapascal. Now, we calculate how much you are going to get here. Someone calculate and give the answer. Whether screen is visible or not?
287.28 megapascal.
Okay, 287.28 megapascal.
28.
Okay, let us compare here. What is the difference of amount you got because of consideration of the affecting factors here? Is it right? So, you can't go for directly 420. Okay, so you need to consider all these factors. I think you got how the entrance limit is going to affect by using these factors. Okay, clear. Okay. So, next is what? Stress concentration effects. So, next is stress concentration effects. So, already you noted, okay, already have noted. So, now the stress concentration factors used for cyclic loading is less than the theoretical stress concentration factor. Okay. That is what it is going to reduce the endurance limit. Okay. It is going to reduce the endurance limit due to stress concentration. Okay. Now, the stress concentration factor used for cyclic loading is less than the theoretical stress concentration factor because of notch sensitivity, okay, of the material. So, yesterday I have noted. So, first you need to find out the fatigue stress, the theoretical stress concentration factor you need to find out from referring design data and do it. Then you need to go for Kf, okay, fatigue stress concentration factor. So, now fatigue stress concentration factor, what you got? You got a Q in bracket Kt minus 1, okay, plus 1. Yesterday got this equation, okay. Now, as the fatigue stress concentration factor is associated with notch sensitivity, so the value of the stress concentration factor is going to reduce the endurance limit of the component or endurance limit of the material. Okay. So, now as you need to consider the value of Q, okay, then you need to consider the theoretical stress concentration factor. Okay. So, then you find out the value of Kf, then you find out value of Kf. Okay. Now, so let us see in equation. So, where they have used Kf, now they have used KTF here, they have used KTF here. Okay. So, now KTF stands for fatigue stress concentration factor. Okay. So it is what KTF. What I noted yesterday, we have noted KTF or KF. We have noted KF, right? We have noted it as a KF, fatigue stress concentration factor. Now you don't bother about the notations, so you can use your own notations, but you must have the idea. So what notation you use it for what purpose? Now some book they have gone for a KF, some book they have gone for KT, okay, KTF, okay. So now some book they have gone for some different notations they are used, okay, but the formula remains the same. Fatigue stress concentration factor equal to, this is what notch sensitivity in bracket theoretical stress concentration factor minus 1 plus 1, okay. So you are going to get the fatigue stress concentration factor, right? Okay. So yesterday I discussed how to get the value or how you can design the components so when they are subjected to fluctuating stresses. So as I suggested, you are going to get a 3 theories here. You are going to get a 3 theories. So one is what the Soderberg relationship, another one is Goodman relationship, and one more is Gerber. That is what Gerber curve or a Gerber line. Now I'll just draw one diagram here. Okay. So it's called the fatigue failure diagram for a general case. Okay, so I'll just draw it. So now these points are failure points. These points are failure points. Okay. So what they have done? So they have conducted a number of experiments on these specimens. Okay. So components subjected to fluctuating loads. So because of these fluctuating loads, you are going to get a fluctuating stress. Again, these fluctuating stress, we have a two here. One is what you need to calculate what is the mean stress or average stress. So then, as well as you are going to get the stress amplitude or variable stress. Okay. Now, so the component is identified in such a way that so sometimes it is also subjected to combination of both. Okay, combination of both. Okay, I think you have noted in fluctuating stress mathematical models. So for some case you have got a sigma m some value here, and for some case you have got the value of sigma a also. Okay, and for some case you got the value of sigma mean here, it is 0, and for some case the value of amplitude stress you got 0, right? You got 0. So all this is because of the magnitude of stress, okay, magnitude of stress as well as its direction, okay. So now this is what a general diagram, so which has been plotted in accordance with the amplitude stress as well as the mean stress, amplitude stress as well as mean stress. Okay. Now this experiment is conducted on different type of materials. So the materials may be of an ductile nature, material may be of an the brittle nature. Okay. So now and safe curve is drawn here, and safe curve is drawn which are exactly below the failure points. Okay. The curve which is get in the line which has been drawn in consideration of exactly below the failure points. So this line is called as a Gerber line. This line is called as a Gerber line. Okay. So some other lines have been drawn here. Okay, so now in this case they have considered linear correlations. Okay, they have considered linear correlation and they have drawn some more lines here. Okay, now the effect of amplitude stress and mean stress. Okay, amplitude stress and mean stress. Okay, if the component is subjected to reversed bending stress, okay, completely reversed bending stress. So what is the value of amplitude stress? Just look out, go back to the diagrams what you noted. Okay, if component is subjected to, okay, completely reversal stress, okay, so what is the value of sigma amplitude and what is the value of sigma mean? Someone give the answer. I will draw the diagram here. Completely reversed stresses. Okay, now this is what maximum. Okay, this is what minimum. So let us go for sigma max equal to 20 megapascal, sigma minimum equal to minus 20 megapascal. So now you quickly calculate and give the value. What is the amplitude stress and what is the mean stress? Someone calculate and give the value. Already I have noted how to calculate the sigma amplitude and sigma mean. Using data handbook, I think equation number 2.5. Someone unmute and give the answer.
So sigma mean equal to 0 and sigma amplitude equal to 20 megapascal.
Right. Okay. Sigma mean equal to 0. Sigma amplitude equal to. Okay. Now, in this case, what happens? So, as the variation of stress takes place, okay, from positive to negative, from positive to negative, so the possibility of fluctuating is more here. The possibility of fluctuating is more, right? So now, if we have an amplitude stress as a maximum, if we have a amplitude stress as a maximum, so then these components are to be designed based on the endurance limit, based on the endurance limit, right? So one more case I think I have given. Okay, so what is the possible of repeated stress? Repeated stress. Now in this case only sigma max is there, 20 megapascal, sigma minimum is 0. Now we calculate what is the value of amplitude stress and mean stress. how much you got? Minus 10 plus 10, or sigma amplitude equal to sigma mean?
Sigma amplitude equal to sigma mean.
Sigma amplitude equal to how much you got? 10 kilonewton, sorry, 10 megapascal for both case.
Yes, sir. For both equal to 10 megapascals.
Okay, 10 megapascal. So now on the situations you just look out. So the component is going to fall in this category. The component is going to fall in this category, right? Okay. Now, so you may get some examples in a such a way that, okay, in a such a way that, so the amplitude stress is equal to 0. The amplitude stress is equal to 0. You may get some examples, you may get some components, okay. Suppose if the component is subjected to, that means the variable stress is 0, variable stress is 0, so then it is a consideration of an static failure. Then it is what? A consideration of static failure. You just look out here. Now this is about sigma equal to 0, so it is going to fall in the category of sigma mean only. It is going to fall in a category of sigma mean. So then you can design the component either consideration of sigma y, either consideration of sigma u. You can consider sigma y or you can consider sigma u based on the material. Okay? Based on the material. Okay? Suppose if the components falls between these two, as you said, now if you consider this case, if you consider this case, sigma amplitude equal to 10 megapascal, sigma mean equal to 10 megapascal. So then the component comes under here. Okay. Now it is subjected to both mean stress as well as amplitude stress. So then you need to design considering any one curve here. If the material is of ductile, then you go for Goodman relation. If the material is brittle nature, means if you need to consider the ultimate strength as a parameter here, then you go for Goodman line. Okay. If the material is of ductile nature, if you want to go for based on the yield stress, then you go for Soderberg relationship. Okay. Then you go for Soderberg relationship. Okay. Now let us go for point here. Let us take this as a point P. Okay. So you need to design a component which is subjected to mean stress as well as amplitude stress. Okay. How you are going to get the relation with respect to the sigma y, with respect to sigma m, with respect to sigma y, sigma a, with respect to sigma e. Okay. Let us go for derivation here. Okay. Let us go for derivation. So now first I will go for a Goodman relation, Goodman method for combination of stresses. So this is also called as Goodman relationship, only Goodman relationship for fluctuating stresses. Now, so now consider the Goodman line here. Okay, consider the Goodman line. You just note on this diagram. This has to be straight line, not a curve. No. Now the straight line which is going to connect from sigma e to sigma u is of Goodman line, so which is of failure stress line, okay, which is a failure stress line, so which has been connected from, so endurance stress to the, or endurance strength to the, so the ultimate strength or ultimate stress. Okay. Now as we need to design the component considering within some safe stress, okay, that is what some safe value. Okay. So now let us take FOS as a factor of safety. FOS as a factor of safety. So now the safe stress in terms of sigma u, okay, the allowable ultimate stress, or you can say, or design ultimate stress. Okay, let us notify this as a sigma ud. Okay, now this is what sigma ed. Okay. Now you just connect the lines. Okay, then you draw the line. Okay, so taking the value of sigma u by FOS as a point D and sigma e by FOS as a point C. Then you just join here. Now this line is what a safe stress line. This line is of a safe stress line. Okay. So now in this case, let us consider sigma e is endurance limit. Endurance limit. Okay. So what megapascal? Next. So sigma u is ultimate stress. Ultimate stress in terms of megapascal. Okay. So sigma m is mean stress or average stress. Okay. So next, sigma a, this is what amplitude stress, or the variable stress. This is what in terms of megapascal. Okay. Next, let us consider FOS as a factor of safety. Factor of safety. Okay. Now let us take a point P. Okay. Let us take a point P here. Okay. So now point P is of design point. Is of design point. Now you have a component which is subjected to the amplitude stress as well as the mean stress. Amplitude stress as well as mean stress. So now let us draw some parallel lines here. Let us draw some parallel lines. Now I will draw the parallel line with respect to the sigma mean here, and I will draw the one parallel line with respect to the sigma a. With respect to sigma a. Now let us identify these points as, I will go for this point as a Q, okay, this point as a R, okay, this point as a Q and this point as a R. Now this is value of sigma m, right? This is what mean stress it is subjected to, and this is value of sigma a, which is subjected to amplitude stress or variable stress. Now if you consider the similar triangles here, if you consider the similar triangles, okay, now if you consider the similar triangles of COD and PRD, okay, if you consider the triangles COD and PRD, okay, so what are the relations you are going to get here? Okay, so let us consider similar triangles here. Let us consider similar triangles. Okay, so consider similar triangles COD and PRD, right? Right. So now in this case, what happens? PR divided by CO. Okay. Now let us consider these similar triangles here. Right? PR divided by CO, which is equal to what? RD divided by RD divided by OD. RD divided by OD. Right? Now let us calculate RD equal to this much portion. RD equal to this much portion. Right? So how you will get RD equal to OD minus OR divided by OD. Okay. Is it right? RD can be calculated here. Now this distance is calculated at OD minus RD. Sorry, OD minus OR. You will get this one. Now you simplify here. Okay. Now you simplify. So what is the equation? So PR divided by CO equal to OD minus OR divided by OD. Okay. OD minus OR divided by OD. Now, what is the value of PR here? Now we can further simplify this equation. I will just move here. PR divided by CO equal to 1 minus OR divided by OD. Right? Now, look out. So PR equal to what here? PR equal to sigma A. Right? So PR equal to sigma A. Right here, sigma A divided by CO equal to what? CO equal to sigma E divided by FOS. Sigma E divided by FOS. This is equal to 1 minus OR equal to what? OR equal to sigma M. Right? OR equal to sigma M divided by OD equal to sigma U divided by FOS. Sigma U divided by FOS. Okay. Now, if write the equations which has to be associated with the amplitude stress or variable stress here. Now, can we simplify this one? Now, just write here sigma A equal to, whether sigma A into FOS is going to come here, divided by sigma E, which please cross check. Okay, otherwise you do one thing. So 1 equal to, okay, 1 equal to sigma A divided by sigma E FOS, okay, plus sigma M divided by sigma U into FOS, right? Now 1 equal to sigma A plus sigma M. I will write here. Now FOS is come on numerator. It is coming on numerator or denominator? It is coming on numerator or denominator? Please give the answer. So now this is the relations you need to find out the by using this theory, okay, by using this Goodman relation, right? Now, as you seen, The fatigue stress concentration factor is associated with the variable stress or amplitude stress. Okay, variable stress and amplitude stress. So let us substitute the factor which is going to affect the amplitude stress or variable stress. Okay. So now KTF or KF is associated with the variable stress or amplitude stress. Okay. Now already you noted, so the endurance stress is affected. Okay, endurance stress is affected. Now it is with the help of these three parameters. Okay, these three parameters. So let us substitute here. Let us substitute in above equation. So 1 divided by FOS equal to, okay, KF into sigma A divided by sigma E ABC plus sigma M divided by sigma U. Now this is the relation used to design the components when subjected to fluctuating loads of brittle material or of nature which has the ultimate stress. Okay, which has the ultimate stress. Now let us look out here. Now 1 by n is 1 by n, okay, kf into sigma A divided by ABC into sigma E plus sigma M divided by sigma U. Okay. Now you just go to the data handbook. Just go to the data handbook. Okay. Now have you got this equation here? Now here, Goodman relation for ductile material. So have you got this equation? KTF sigma A divided by ABC into sigma En, okay, plus sigma M by sigma U equal to 1 by N. So now instead of FOS they have gone for N notation here. Okay. Now N equal to what? N equal to factor of safety. Factor of safety, right? So equation number it is 2.21a. Question number 2.21a, okay, from your design data handbook. Now similarly, now you derive equation for Soderberg relation. Okay. So what will you get equation there? Now this is 1 by n equal to, okay, kf into sigma A divided by ABC into sigma E, okay, plus sigma M divided by sigma Y. You are going to get the equation. Okay. From design data handbook you just cross check equation number 2.21c. 2.21c. Okay, you will get this equation. Again you have to consider similar triangles. Okay, so note on the values for here. I will just highlight here. Now you need to replace sigma y by FOS. That's all for Soderberg. Now instead of sigma u, you need to go for sigma y. Okay, then you need to write here sigma y equal to ultimate stress, sigma y equal to ultimate stress, right? So you please try that equation and solve it. So let us go for you have another two parameters here, KT. So I think this is a KT equal to, again, it is a stress concentration factor. KT.
Hello, excuse me, sir.
Hello.
Sir, we have another class, sir. Next.
Okay. You just provide the attendance. Okay. Just give the attendance. Sorry.